Here we want to look at velocity as a rate of change. So velocity as a rate. This goes with problem set 1 and the introductory problem sets. Question: at 6 meters per second, how far do we travel in 7 seconds? What does 6 meters per second mean? It means the change is 6 of these for every one of these. The change is 6 meters for every second. We're moving at 6 meters per second. So to figure how far that is in 7 seconds, well, 6 meters every second for 7 seconds implies a displacement of 42 meters. Now let's note that delta S, which is designated by backward apostrophe ds, I have to use a backward apostrophe d to designate a delta. This is because if you bring an HTML document into the wrong word processor or whatever, you're going to get a D instead of, if I use the delta symbol, you'd get a capital D instead of a delta. And we can't have that because capital D is going to have a completely different meaning for many of you. Okay, so we have to use a backward apostrophe D for delta, but when you write out your problems, don't use a backward apostrophe D unless you're doing this in a word processor. Okay, when you write things out by hand, use the delta symbol instead of a backward apostrophe D. That's in general. Anytime you see a backward apostrophe D, that means a delta. Okay, anyhow, that's how we designate the thing on a home page, delta S. S is the position, delta S is change in position. So we see that the change in the position of the object is 42 meters. Now, that's one way of thinking through the solution, a way of conceptualizing the solution in terms of what 6 meters slash second means. It means 6 meters per second, 6 meters every second, so that this reasoning ought to be fairly obvious. Now, if we move at 6 meters per second for 7 seconds, we can, well, we're going to multiply the 6 meters by the 7 seconds. If we multiply, the 6 meters per second by the 7 seconds. If we multiply 6 meters per second by 7 seconds, we get 42 meters per second. 6 times 7 being 42, we have the meters per second. And then we have another second, which we'll write as second over 1 in the manner that we do with fractions when we want to multiply two fractions. Then we multiply numerators and denominators. But we can see that the second here will divide the second here. The 1's not going to make any difference. We end up with meters per second times second just being meters. So this unit calculation is very important. Another way of looking at the situation is shown here at the bottom. And let's zoom in just a little bit so we can read a little better. Okay, now delta S, in the terms of rates, we're going to see that this is the change in our quantity, the quantity being position. V, the velocity, is the rate of change of position with respect to time. It's the rate at which position changes over time, the number of meters per second. And delta T is the time duration over which this velocity is going to apply to give us this delta S. So we can write the formula, delta S equals V delta T. We shouldn't write this formula, though, without understanding all of this very well. And when we write out the result, we get 6 meters per second times 7 seconds equals 42 meters. We should also try to think in terms of pictures. So let's move in a little closer so we can see this picture. Here's a picture of 6 meters corresponding to 1 second's worth of motion, then another 6 meters, another second, and so forth. We have 7 6-meter arrows here, and they add up to a 42-meter arrow, showing us why 6 meters every second gives us 42 meters in 7 seconds. A flow diagram of the situation. We have velocity, we have time interval, and we have our change in position. All three quantities are interrelated in that we can get any one quantity from the other two. In this case, we had V and delta T. We used that to get delta S. Had we had delta t and delta s, we could have used that to get v, as we'll see. And had we had delta s and v, we could have obtained a delta t, as we'll see in the next couple of examples.